section 6.6, solving radical equations. All right, we're wrapping up our chapter here, and we're going to be seeing some of our properties that we've been working with radicals and properties of exponents coming together here to help us come up with solutions to problems that involve radicals or exponents, looking for that variable of x or whatever it is. We're going to start out here with the radical side, and then later on we'll get to the exponential side of things and how we can take care of it. We have a little acronym that we use to help us with the process of solving radical equations and rational exponentials. And the acronym is IRS, and it stands for isolate, raise, and solve. And there's our process that we're going to use to help us come up with these variables, the solutions to these equations here, these radical equations. So IRS, isolate, means to get the radical by itself. So much like when we're solving an equation and we want to isolate the variable, and we do that through removing constants that are adding or subtracting, and then removing coefficients that are multiplying or dividing. We do the same thing with radicals. We want to make sure we remove anything that's adding or subtracting with the radical, then get rid of any coefficient multiplying with that radical, and then we have an isolation. And then we can then undo the radical, and the undoing process is done by raising to a power. So you undo a radical by raising to whatever its nth power is. So if I have a square root, I'm going to raise to a square. If I have a fourth root, I'm going to raise to a power of 4, and so on. And then from there, we were able to undo the radical and solve. So let's try a couple of these here. First example, isolation, raising, solving. The isolation part is already done. The square root of 5x minus 9 is already by itself. So we're ready at this point to go ahead and raise. And that means undoing a square root takes us into squaring. And we get 121, and then we now solve this like we would just in a generic equation and come up with x equals 26. So it's pretty straightforward. We're going to skip B here. We're going to go to C, go to something a little different. Now we have a cube root, and we have a cube root where we've got a constant being added to that cube root. So in this case, we're going to have to move that over first. So after we have moved that 1 over, we've now isolated our cube root. We're now ready to raise to the power. This time we're not squaring, but we're cubing to undo the nth root of 3 here. And again, once you get to this point, it's just a solving equation problem. We get x equal -3. And we can check these. Before we can move on, maybe we peak at -3. We plug -3 back in. Let's see if we stuck a -3 in here. We get the cube root of -8, which is -2, and -2 plus 1 equals -1. So, yeah, that one works. Good idea to check our work here. Rational exponents, they behave the same way, except we don't have radicals, we now just have powers. We still use the same procedure. So we're going to isolate, we're going to raise, we're going to solve. But what's different here is, while we were undoing powers in the last problems, we're now undoing these fractional exponents, which really means we want to make our fractional exponents become 1. And in order for us to do that, we use reciprocals. For example, I have x to the 2/3. Now I want to make that x to the first. Well, if I raise 2/3 to the 3/2, that's giving me my x to the first value. So that's what we're going to do here. We're just going to use reciprocals to undo these fractional exponents. All right, in the first example, we have a 7 and an x to the 3/5. And just again, paying attention to the fact that the x is the base, not the 7. 7 is just a coefficient. So I'd first divide that 7 out. And then I'm left with x to the 3/5 power is equal to 8. And now I will undo this power of 3/5 by raising to the 5/3 power. That gives me x. And then I have 8 to the 5/3. So I can look at that as the cube root of 8 raised to the 5. Or I could have looked at that as 8 to the 5th cube root. Well, this one is much easier for us to do without the aid of a calculator. You know, the cube root of 8 is 2, so x is equal to 32. All right, let's try these next couple here. A little different. So the isolation process first involves us moving that 9 over. And now we've isolated our base and exponents, so we can now raise to the reciprocal power. We get x minus 4 is equal to, again, you have a choice. You do 25 cubed and then take the square root of that number, or you can take the square root of 25 first and then cube it. That's a little easier. So doing this, we get x minus 4 is equal to 5 cubed, or 125. And then add that 4. And voila, x equals 129. Good stuff. What about here? We're already isolated in this step, so we're just ready to raise. 3x plus 4. Again, I'm going to do the root first, so square root of 16 is 4, and 4 cubed is 64. And now 3x is equal to 60 by subtraction, and x is equal to 20. And there we go. So there's our process for using the IRS, isolate, raise, or solving system for radicals and for rational exponents. Those examples that we looked at previously only had a variable on either the left or the right-hand side of the equation. What happens when you get variables on both sides is you get an opportunity to see what's called an extraneous solution. Extraneous. These result because when I do square a square root to undo it, and I have a variable on the other side that I am also squaring, I create a quadratic. That quadratic then in turn gives me two answers, more than likely two answers, two real solutions. And one of those real solutions may not work when I plug it back into the original. So be careful when you have variables on both sides. Be careful when you have two different radicals on both sides of the equation. So we're going to check out for the extraneous solutions here. All right, we've already isolated our root, so we're ready to square. Now what's different is on the right-hand side, whatever is over there, in this case had an x minus an 8. I am squaring the entire thing. So as a polynomial, I'm squaring that as a binomial squared. I am not doing x squared minus 8 squared. That is a no-no. We're squaring the entire polynomial on that side. So this becomes a x minus 6, and then raising x minus 8 to the power 2, foiling, I get x squared minus 16x plus 64. And now we want to we got an x squared term, and we know that solving quadratics involves me getting 0 on one side. So I'm moving the x to the other side. I'm going to move the negative 6 to the other side. This one through subtraction. This one through addition. I get 0 is equal to x squared minus 17x plus 70. And now we go back to using our factoring skills. So we're never really done with that, right? We started with it, we reviewed, we see it again with quadratics, we see it with polynomials, finding roots, zeros. Here we are again. So we got to really make sure that factoring is down solid when I'm working with this. So I get two possibilities because of the zero product property, that x is equal to 10 or 7. Now I got to make sure that they both work. What if x was equal to 10? Then I would have, in the original problem, square root of 10 minus 6 equaling 10 minus 8. So the square root of 4 equaling 2, and 2 equals 2, that one checks. So x equal 10 works. Let's go see if x equals 7 works. X equals 7 would be the square root of 7 minus 6 is equal to 7 minus 8. So the square root of 1 equaling negative 1. And the positive root, these are positive roots given their principal roots. So that is not true. And therefore, x equals 7 is an extraneous solution. So you can just do that. That's indicating that you understand that although we found a solution through the process of squaring both sides, one of them will not work. About, let's just pick one of these to work with. Isolated already on the right-hand side, so we're ready to square. X squared minus 4x plus 4, x plus 10. Moving everything over to the left-hand side, x squared minus 5x minus 6, and then an x minus 6 and an x plus 1 will be my factors, giving me zeros of 6 or negative 1. And then once again, we can plug in and check. X equals 6. 6 minus 2, does that equal 6 plus 10 root? So 4 equals square root of 16, 4 equals 4, we are good. X equals negative 1. Negative 1 minus 2, does that equal negative 1 plus 10 under the square root? Negative 3 does not equal 3, and therefore negative 1 is my extraneous solution, leaving me with x equal 6. Let's try these again. Go ahead and pause and work them out as you need. See if you're okay with this. Get x squared plus 2x minus 3 this time. And x plus 3x minus 1. Zero product property, negative 3 or 1. Negative 3 plus 2 is negative 1. Negative 3 times 2 is negative 6. Negative 6 plus 7 is 1. The square root of 1 is 1. And 1 does not equal negative 1. So this is my extraneous solution right here. Let's just make sure 1's going to work. So 1 plus 2 is 3. 2 plus 7 is 9. Square root of 9 is 3. And 3 equals 3. Therefore, x equal 1 is my solution to this. Then we get the situations where I have multiple roots. And in this case, when it comes to the isolating part, if I'm supposed to isolate something that has multiple roots, I can't move a radical, well, I can move a radical around to the other side of an equation, but I really won't create a single radical unless those are radicals would have the same radicand. So if I had, for example, the square root of x plus 6 equal to the square root of x plus 6, or I'll say minus square root plus 3, well, since these are the same radical, they are like terms, and this would become 2 times the square root of x plus 6 is equal to 3, and then I could work this problem out isolation-wise. But here in this problem, we have different radicands, which means I can't combine them in any way. So the squaring twice, I want you to think of IR, S. We're going to isolate and raise, and then we're going to re-isolate the other root that we get, then raise, then solve. So we're going to add a little IR here in front of our IRS acronym to help us with this. These problems take a little bit of time. They take a little bit of space, so give yourself some of that. And it's a good review on foiling. It's a good review on working with perfect square trinomials. So here we go. We're going to isolate. It's already done on the left-hand side. So now when I square, notice that I'm squaring as a binomial the square root of 11 minus x minus 3. And I want you to look at this as if it was, let's just generically call it some binomial a minus b squared. A minus b squared, we know, is the perfect square trinomial of a squared minus 2ab plus b squared. This is the model that I will use for these binomials that involve roots. So let's see if we can work this out here. So on the left-hand side, x plus 6. On the right-hand side, a squared. This is your a. This is your b. So if I were to square 11 minus x, that just becomes the square root of 11 minus x. I just get 11 minus x. Then I do this twice ab thing. So I'm going to have minus 2 times a and b. And then, again, my plus b squared, meaning just gives me a 9 there. So I'm just foiling out this binomial, which looks funny because it's got one of its terms as a square root. But the process is not any different. All right, on the right-hand side, we see that we have some work to do, so let's just go step by step. I have some like terms of 11 plus 9, so I can make a 20 here. And then minus an x, and then I get negative 6 times the square root of 11 minus x. Well, the 20 and the 6 can move over to the left-hand side. So we're trying to isolate that radical. So here's where the IR part came in. We isolated the first time, we raised, now we're isolating again. So I move the x over, I get 2x, I move the 20 over, I get negative 14, and now this is equal to negative 6 times the square root of 11 minus x. Isolation, let's get rid of that negative 6, so we're going to divide, and I'm going to show the division of the entire binomial there on the left-hand side. Don't worry about simplifying it. So I get 2x minus 14 over negative 6 is now equal to the square root of 11 minus x. I'm now ready to isolate and raise. Now we're raising, both sides we're squaring. Now notice on the left, you're squaring a binomial over an integer value. So you have a rational expression there. Which means, think about my properties rule. I'm going to be squaring both the top and the bottom. So it's like saying I have 2x minus 14, that quantity squared, over negative 6, that squared, is equal to now 11 minus x. Well, the 2x minus 14, it's another binomial squared. Didn't we just do that? We did, so we do it again. 4x squared minus 56x plus 196 all over 36 is equal to 11 minus x. Here, let's just get rid of that 36. So let's multiply the entire equation by 36. And I get 4x squared minus 56x plus 196 is equal to 36 times 11 minus x. So this becomes 396. Minus 36x. All right, we've got a quadratic where on the left-hand side is an x squared. Let's leave it. Let's move all of these to the other side. So I got a negative 56 x. 4x squared. Negative 56 plus 36 is minus 20 x's. 196 minus 396 is negative 200, and now this is equal to 0. I can see that they all are divisible by 4. I get x squared minus 5x minus 50 is equal to 0. Factors x minus 10, x plus 5. That gives me zero product property saying that I have a potential of 10 or negative 5 as my solution. Now I got to go back and check that. And if we check the 10, let's go check the 10 back into the original. 10 plus 6 is 16, square root of 16 is 4. 11 minus 10 is 1, square root of 1 is 1. So I have a 4 on the left-hand side. I have a 1 minus a 3, which is a negative 2 on the right-hand side. So 10 looks to be extraneous. Let's go check negative 5. Negative 5 plus 6 is 1. Square root of 1 is 1 on the left-hand side. 11 plus 5 is the square root of 16, which is 4. And 4 minus 3 is also equal to 1. And so negative 5 is our solution for what x is. So take a little bit of time with those. Don't rush through them. Try another one here. Isolation is already done on the right-hand side, so this time I'm going to square here, and I'm going to square here, and through my squaring of a binomial, I get x plus 6 from squaring the square root of x plus 6. And then I have 2 times square root of x plus 6 times 2. Here's my 2ab part. And then my b squared part equal to 10 minus 3x. We got an x plus 6 plus a 4 root x plus 6 plus a 4. Go ahead and move things around to isolate. So I have an x plus a 10 on the left-hand side, combining my 6 and 4. Moving everything over, I get 4 times the quantity of x plus 6 is now equal to 10 minus 10, which is 0. And then negative 3x minus x, which is negative 4x. And then dividing by 4, we get that radical x plus 6 is equal to negative x. So here, we're ready to raise. We've isolated again, now we're raising. And we get x plus 6 is equal to x squared. Move everything over to the right-hand side. 0 is equal to x squared minus x minus 6. And we get an x minus 3, and then x plus 2 is equal to 0. So x is equal to a 3 or a negative 2. We go plug them back in. 3 plus 6 is 9, square root of 9 is 3, and 3 plus 2 is 5 on the left side. 10 minus 9 is 1. Square root of 1 is just 1. So it doesn't look like our 3 works. That could be our extraneous solution. Let's go check the negative 2. Negative 2 plus 6 is 4, square root of 4 is 2, and 2 plus 2 is 4 on the left. 10 minus 6 is 4, and square root of 4 is also 2. And so that becomes our solution. A couple application problems going along with this. The velocity of a free-falling object is given by v is equal to the square root of 2gh. V is the velocity in meters per second. G is our acceleration due to gravity in meters per second squared. H is the distance in meters and the object that the object is falling. The value of G depends on which body or planet is attracting the object. If an object hits the surface with a velocity of 30 meters per second, from what height was it dropped in each of the following situations? All right, so we're going to put ourselves on different planets, but they have different gravitational constants. On Earth, it's 9.81 meters per second squared, so that gives us our G value. And we're looking for, we go back to the equation, what height? So we're looking for our H, that's our unknown here. So we start with our equation. V is equal to the square root of 2gh. And in our problem, our g value is 9.81 meters per second squared. And we've been given a velocity of 30 meters per second. 2 times 9.81 h. So we have 30 is equal to the square root of 18 plus another 1.62, so 19.62 h's. And now I'm ready to undo that radical, so we're going to square both sides. And get 900 is equal to 19.62 h. And then divide that 900 by 19.62, and we will get 45.87. And we were looking for, in this case, a height, and we were given information in meters, so we have a height of 45.87 meters. So there we are undoing our radicals there with our radical property. All right, here are a couple other ones you can try. Again, just check back with the answers a little bit later if you're interested. So we're using the same equation, v equals the square root of 2gh. Still using 30. Now our g is 1.57. For 86.62. All right. We'll go ahead and leave it there. I hope that was helpful. See you next time.